Okay, so let's move on to section 4, the last section of the chapter. And once we're done with that, we're going to take 2 days on this. Then we'll do some review, and after that we'll do a quiz on the last half of the chapter, which includes section 3, starting with PV equals nRT, and going through real gases, and then what we're going to cover today and tomorrow. And we'll do a quiz on all that. You'll recall we already had a quiz on the first 2 sections of the chapter with all the gas laws. So we'll split the chapter in half and do 2 separate quizzes. Now, section 4 deals with 2 major issues. What happens if you mix gases, and how can you measure the motion of gases, which we'll look at what that means tomorrow. But let's look at gas mixtures. So first of all, we don't care about their little we relate to you thing. The first big issue in this section is Dalton's law of partial pressures. Now, if I have a sample of just a gas, say oxygen gas, we can talk about the pressure of that gas. And you can calculate that pressure from PV equals nRT, like we've been doing. But what if I have 2 gases mixed together, say nitrogen and oxygen mixed together? Then, yeah, we have a total pressure of the gases, but how much of that pressure is contributed by oxygen? And how much does nitrogen contribute to the pressure? Those individual pressures of the gases are called partial pressures. And so we want to know how they relate to each other and how they relate to the total pressure of the gas. Now, to work through this, we know that gas pressure comes from the molecules colliding with the walls of the container. So if I have a steel canister with gas in it, as the molecules collide with the steel canister, they're going to be pushing against it and creating pressure. More collisions means more pressure, and the faster collisions, meaning higher temperature, means more pressure. Okay, so the number of particles determines the pressure. Also, the average kinetic energy, or the temperature, determines the pressure. Those were some of our gas laws. But notice as you add more molecules or as you make them hotter, the pressure increases. Now, what if I'm working with 2 gases mixed together? Well, they're obviously at the same temperature. So they have the same kinetic energy. That's not going to affect anything. Doesn't really matter what they are. We talked about that already, the partial pressure. Now, it turns out that in a mixture of gases, yes, you can measure the partial pressure of each gas. Nitrogen gas molecules are hitting the container, contributing some pressure. Oxygen gas molecules are hitting the walls of the container, contributing their pressure. Each one is a partial pressure. The total pressure inside the canister is just the sum of the 2 collisions, the nitrogen collisions plus the oxygen collisions. So the total pressure is just adding up all the partial pressures. So that makes life easy. The example, and by the way, right here they say that, the total pressure of any gas, their example they're using is air, is the sum of the partial pressures of all the components. And that's Dalton's law right there. They'll probably wait till the next slide to tell you that or something. The example they use is dry air. What we mean by that is air with all the water vapor taken out, because water vapor varies so much from day to day and place to place that it would change things too much. So we usually just measure dry air. So notice they show you the percent of nitrogen, oxygen, CO2, and then other gases in the air. Most of our air is nitrogen. Next most prominent gas is oxygen, then some CO2, and then a lot of other gases make up a small percentage of our atmosphere. Now, notice the total pressure of the air is standard pressure, 101.3. They give you one more sig dig here, kilopascals. If we look at just the nitrogen in the air, it contributes 79 point whatever kilopascals. Just the oxygen contributes 21 point whatever kilopascals, and so on. If you take each of those partial pressures and add them all up, you get the total pressure of air, 101.325 kilopascals. So this is just showing that in a mixture of gases, which our air is, you take the partial pressure of each individual gas in the air, you add them all together, and you get the total pressure of air, which we know from standard pressure. And that will hold true in general. The total pressure of any mixture is just equal to the sum of all the partial pressures. Okay, and that's right there a statement of Dalton's law. This is like the easiest law ever. If you have two gases mixed together, take the pressure of both gases, add them up, you got your total pressure. Okay? Now, notice, just like in all our other gas laws, we have these little cautions. It's got to be at a constant volume and a constant temperature. If I'm mixing gases and I suddenly change the temperature, obviously the pressure is going to change. If I compress the volume, obviously the pressure is going to change. So let's not do that. Let's only change one thing. So if I don't mess with the volume and the temperature, I mix two gases together, each at partial pressure of one gas plus partial pressure of the other gas. The total pressure when I mix them will just be the two partial pressures added up. Or mathematically, P total equals P1 plus P2 plus P3 plus and so on, where you have gas 1, gas 2, gas 3, gas whatever. If I only have two gases, I obviously only need these first two. If I have 10 different gases, I need up to P10, which would be a pain in the butt, but not difficult to do mathematically. The total pressure equals the sum of all the partial pressures. So if I know the partial pressures of my gases in my mixture, I can add them up and get what the total is going to be. Probably a more realistic question is, I know the total pressure. I know the partial pressure of some gases. Find the partial pressure of the other gas. So here's an example they use with diving gas mixtures. Deep divers can't use nitrogen and oxygen because the pressure has to be too high and they get nitrogen narcosis. The nitrogen diffuses into their bloodstream, gets in their brain, and makes them kind of like drunk, which is not good when you're deep underwater. So they use a mixture of helium and oxygen instead called heliox. So you have a heliox mixture in your little air tank that's at 500 kilopascals, about 5 times normal air pressure. It's a mixture of helium and oxygen. Notice what they do is they put around 400 kilopascals of helium in there and 100 kilopascals of oxygen in there. The total pressure is just equal to the sum of the two partial pressures. So notice if I had given you the 500 kilopascals and I had given you that helium is at 400, you could easily find that oxygen must be 100. All right, but that's how you deal with Dalton's law. Okay, so here's an example. They give you air containing blah, blah. What's the partial pressure of oxygen at this total pressure? So they give you the total pressure, and then they tell you that all the other gases are this, this, and that. Nitrogen's this, carbon dioxide's that, miscellaneous gases is that. So they're giving you the total pressure, and they're giving you partial pressures of all the other gases. They want you to find the partial pressure of the last remaining gas, oxygen. Well, I don't know why they're doing this example. They already gave you the answer on a few slides back, but whatever. Notice total pressure equals partial pressure of gas 1, oxygen, plus partial pressure of gas 2, gas 3, gas 4, the miscellaneous ones. And now, what do we know? We know the total pressure is 101.3. We're looking for partial pressure of oxygen. We know the pressure of the other gases, nitrogen, CO2, and miscellaneous. We know all those. So simply plug everything in. The only unknown is pressure of oxygen. So do the advanced math of subtraction to find it out. All right. So plug in the values, find the pressure of oxygen, and you get 21.22 kilopascals. This is the easiest thing ever, isn't it? Well, yeah. Does the answer make sense? Well, yeah, because it's less than the original, so it must be true. One last example, then I'll stop because I promised Hunter I'd keep this at 10 minutes. Here they use scientific notation, which is kind of annoying, but again, we can live with that. We have a scuba tank, has a total pressure of this ugly number, 2.21 times 10 to the 4th. If they tell us that nitrogen is this, 1.72 times 10 to the 4th, and oxygen is that, what's the partial pressure of any leftover gas in there, whatever else they put in there? Well, again, we got three gases, nitrogen, oxygen, and the other gas. And we know the total pressure. So we know the total, we know two of the partial pressures. Solve for the last unknown partial pressure. So there we go. P total equals P gas 1 plus P gas 2 plus P gas other. Plug in your numbers, solve, and you get this, which is 259 kilopascals, because who needs scientific notation there? So that's Dalton's law. We're going to leave Graham's law for tomorrow, and I'll give you a worksheet with a few problems of these just to make sure you got it, and then we'll move on from there. I went 35 seconds over, Hunter, so we'll have to live with that.